Welcome to the Snoozy Scientist, where we gently wander through the mysteries of science, one sleepy yawn at a time. Tonight, we are drifting inward into the forbidden depths beneath our feet, a hidden world that stretches nearly 4,000 miles inward, a place so vast, so unreachable, that it remains more mysterious than the moon. Beneath your feet lies nearly 4,000 miles of mystery. And yet humanity, for all its machines, has only reached just 7.6 miles of it. If Earth were sliced open like an apple, the crust we call home would be thinner than its peel. Every mountain, forest, and ocean, everything we've ever known, rests on less than 1% of the planet's true body. And what waits below defies imagination. At the core, pressures rise to more than 3.5 million times greater than the air pressing on you now. Temperatures climb nearly as hot as the very surface of the sun. And yet, despite the impossibility of reaching these depths, scientists have found ways to observe what's down there. But we must ask, what's hiding in the deepest parts of the earth? How can we know what no human hand has ever reached? And could our own planet still be keeping secrets too vast, too strange for us to fully understand? Tonight, we'll sink gently into this hidden world, exploring the most extraordinary discoveries ever pulled from the silence beneath us. But before we begin, if you find peace in these gentle journeys where science drifts like a lullaby, I'd be so grateful if you gave this video a soft like or tap subscribe so that more curious dreamers can join us here. And if you'd like, let me know in the comments where you're listening from tonight and what time it is there. It's always such a joy to see how far this little sleepy corner of science can travel across the world. Now, take a slow, deep breath, let your body soften, and let's begin our descent into the forbidden depths beneath our feet. When the ground trembles beneath our feet, we often think of earthquakes as destructive, chaotic moments. Streets crack, buildings sway, and the earth reminds us of its raw power. But to scientists, each earthquake is more than an event on the surface. It is a kind of natural flashbulb, a burst of energy that lights up the hidden interior of the planet. Imagine striking a bell and listening closely to how it rings. The pitch and tone can tell you about the thickness of the metal, the presence of cracks, or even the shape of the object itself. Earthquakes work in a similar way. When they occur, they send vibrations rippling through the planet in every direction. These waves travel down into the earth, passing through layers of rock, shifting as they move from one type of material into another, and bending around boundaries we cannot see. There are two main types of seismic waves: primary waves and secondary waves. Primary waves are the fastest, moving like a push and pull through the rock, squeezing and stretching as they travel. They can pass through solids, liquids, and gases. Secondary waves are slower, moving side to side like the motion of a shaken rope. They can only move through solids. This difference is crucial because when waves vanish, slow down, or suddenly change speed, they leave behind clues about what lies deep below. Seismologists, the scientists who study these vibrations, place sensitive instruments called seismometers all over the world. These instruments can detect the faintest tremors, even from earthquakes that happen on the other side of the planet. By comparing the arrival times and behaviors of these waves, scientists can start to sketch out what the inside of the Earth must look like. The method they use is called seismic tomography. The word might sound complicated, but the idea is surprisingly simple. It works much like a medical scan, where doctors use X-rays to see inside the human body without opening it. In the case of Earth, seismic waves act as the X-rays. When an earthquake sends out energy, it is as though the planet has been illuminated from within, and seismometers record how that light travels and bends. With enough recordings from enough earthquakes, scientists can piece together a three-dimensional picture of the planet's inner structure. In this picture, the crust shows up as thin and fractured, with patches where waves move quickly and other places where they slow down. Beneath that, the mantle appears as a vast zone where waves bend and shift, revealing currents of stone creeping slowly over millions of years. Deeper still, the waves behave in ways that would be impossible if the entire core were solid. The sudden disappearance of secondary waves and the slowing of primary waves revealed something extraordinary. The outer core must be liquid. Later, faint echoes bouncing inside the planet showed that deeper still, there is a solid heart. All of this knowledge came not from drilling or direct contact, but from listening to vibrations. One of the most remarkable aspects of this method is its patience. Earthquakes are not predictable. They arrive when and where they please. Each time one occurs, scientists gather the data like scattered puzzle pieces. With enough earthquakes, the picture sharpens. Seismologists have now cataloged millions of tremors, each one adding another stroke to the portrait of Earth's hidden world. This technique is our only true window into layers beyond the crust. No drill can survive the heat or the crushing pressure that waits even a few dozen miles below. No probe can burrow into the mantle or core without being destroyed. Yet through seismic tomography, we can see patterns that would otherwise be invisible. Ancient slabs of crust swallowed into the mantle, plumes of hot rock rising from the depths, and even mysterious zones at the boundary between mantle and core that defy easy explanation. All of these are revealed by the patient study of ripples moving through the earth. It is a reminder that even in silence, the planet is speaking. Every earthquake, from the smallest tremor to the mightiest quake, sends out signals. And hidden within those signals is the story of a world we may never touch, but can still begin to understand. In the 20th century, while scientists listened to the whispers of seismic waves to map the unseen interior of the Earth, others attempted a more direct path. If we could not rely only on the planet's natural tremors, why not drill down and touch the hidden world for ourselves? The boldest of these efforts took place in a remote corner of northern Russia, on the windswept Kola Peninsula. There, in 1970, a team of Soviet scientists began an audacious project to dig the deepest hole ever attempted by human hands. The site was unremarkable at first glance, little more than a collection of rigs, pipes, and control rooms. Yet beneath that modest ground, machines began to bite into the crust, spiraling deeper and deeper with every passing year. This was the Kola Superdeep Borehole. For more than 2 decades, engineers pursued the dream of reaching Earth's mantle, the layer that lies beneath the crust and stretches nearly 1,800 miles downward. They knew the mantle itself was out of reach, but the hope was to push past the crust and glimpse the boundary. No one had ever seen such depths directly, and the possibility of drilling into that ancient rock carried a weight of wonder. The borehole was not a single shaft, but a cluster of branching tunnels that twisted downward, each new branch pushing deeper as technology allowed. By 1989, the deepest branch had reached more than 7.5 miles beneath the surface, setting a record that still stands today. To imagine the scale, picture a mountain taller than Mount Everest, but inverted, its peak plunging into the earth instead of rising into the sky. Yet even this staggering depth was humbling. The crust beneath the Kola site is estimated to be at least 20 miles thick. The project, for all its triumphs, had only scratched 1/3 of the way through. It was as though humanity had set out to cross an ocean and managed only to step a few paces from the shore. Still, the discoveries made there were startling. Scientists expected the temperature to rise as they descended, but the heat was far greater than predicted. At the bottom, instruments measured temperatures close to 180 degrees Celsius, hot enough to boil water in an instant. This intense heat softened the surrounding rock, causing it to behave less like a solid and more like plastic. The deeper the drill went, the more difficult it became to cut further as the rock walls tried to close around the bit. The rocks themselves were not what geologists expected either. At such depths, they found fractured, broken layers where they had anticipated solid granite. These cracks were filled with water, not surface water that had trickled down through the soil, but ancient water trapped within the minerals themselves. Its presence defied earlier models of the crust, revealing that the deep earth held hidden reservoirs that no one had imagined. The borehole also brought up microscopic fossils from layers more than 4 miles deep, tiny remains of single celled organisms, long extinct, that had once thrived in shallow seas. Their discovery revealed that life's imprint can be carried down into unimaginable depths, sealed away in stone for billions of years. Despite these revelations, the drilling grew more difficult with every mile. Equipment failed, drill bits snapped, and the rising heat strained both machines and patience. By the early 1990s, after more than 2 decades of effort, the project was abandoned. The hole was sealed, the rigs dismantled, and the site left to rust in silence. The Kola Superdeep Borehole remains the deepest artificial point on Earth, yet it is also a reminder of our limits. 7.5 miles is a marvel of engineering, but it is nothing compared to the nearly 4,000 miles that stretch to the planet's core. The thin crust, fragile and cracked, proved impossible to pierce. Humanity's greatest attempt to touch the depths barely left a mark. When people look at the ground beneath them, there is often a sense of stability. Soil feels firm underfoot, mountains rise solid and immovable, and stone seems eternal. It is easy to believe that the crust of our planet is a foundation, something strong and unshakable. Yet when scientists began to map the outer shell of Earth, they found something very different. What appears solid is in truth delicate, fractured, and fragile. The crust, the surface upon which all life depends, is astonishingly thin when compared to the planet as a whole. If Earth were an apple, the crust would be no thicker than the peel, while everything beneath remains hidden from direct touch. Its thickness varies depending on where you stand. Under oceans, the crust is only about 3 to 5 miles deep, a paper-thin sliver of basalt that lies beneath the water. Under continents, it stretches deeper, perhaps 20 to 40 miles thick, but even there, it makes up less than 1% of Earth's volume. This outer shell is not continuous. It is broken into enormous slabs, known as tectonic plates, that fit together like the shattered pieces of a puzzle. These plates drift slowly across the surface, colliding, pulling apart, and sliding past one another. Their movement is so gradual that it is invisible within a single lifetime, yet across millions of years, it sculpts mountains, opens oceans, and carves valleys. The jagged scars of earthquakes and volcanoes mark the edges of these plates, constant reminders that the surface is not still, but restless. The crust itself is made of two very different kinds of rock. The oceanic crust is mostly dark, dense basalt, born from magma that wells up at mid-ocean ridges and hardens in thin sheets. Continental crust is lighter, filled with granite and other less dense rocks that allow continents to float higher than the ocean basins. Together, these two forms of crust create the landscape of Earth as we know it, the continents rising like rafts above the seas, surrounded by the vast basins of oceanic rock. But what makes the crust remarkable is not its strength, but its fragility. It is cracked through and through, riddled with faults that can shift without warning. When pressure builds along these fractures, it is released as earthquakes, shaking the ground with sudden violence. Volcanoes, too, erupt through weaknesses in the crust, releasing molten material that has risen from the mantle below. The crust may feel like a shield, but it is full of openings where the energy of the deep earth pushes through. For all of human history, people have built their lives upon this fragile shell, rarely aware of how delicate it truly is. Entire cities stand on fault lines where the crust is grinding and slipping. Islands rise in the middle of oceans where magma breaks through and hardens. Even mountains, which seem the very image of permanence, are the result of slow collisions as plates push against each other, crumpling the crust upward like paper. Seen in this light, the crust is not the foundation of the planet at all. It is only a skin, a thin layer stretched over far greater forces below. Beneath it lies the mantle, a vast region of rock that, while solid, is hot enough to flow slowly over time. It is the mantle that carries the plates of the crust on its back, shifting them like rafts on a restless sea. The crust is more like a delicate scab that hides the fire underneath, a thin covering over a body still alive with movement. The truth of this fragility is humbling. What we walk on, what we call solid ground, is a thin and fractured veneer. Every step we take rests on a surface only a fraction of the planet's size, a surface always in motion, always at risk of cracking open. The crust is our home, but it is not secure. It is not the heart of the earth, nor its strength, but simply its outermost skin, fragile and temporary compared to the churning life beneath. Like a skin stretched over fire, it hides the deeper workings of the planet. It shields us for now from the immense heat and pressure below, but it also bears the marks of that hidden world. The cracks, the quakes, the eruptions, all remind us that what we see is only the surface of a far more mysterious body. And to understand what lies beyond this thin shell, we must descend further into the mantle itself. Beneath the crust, past the fractures and plates that shape the surface of the world, lies the mantle. This vast layer of Earth extends for nearly 1,800 miles into the planet's body, making it by far the largest region inside. Though it lies hidden, the mantle holds most of Earth's volume and mass. It is the great middle realm of our planet, connecting the fragile crust above to the mysterious core far below. For many years, people imagined the mantle as a fiery ocean of molten rock, a place where lava swirled freely under the crust. The truth is more subtle and more fascinating. The mantle is solid rock. If you could hold a piece in your hand, it would look and feel like any other stone, yet over the span of millions of years, it behaves in ways no ordinary rock does. Heat and pressure transform it into something that can bend and flow, not quickly like water, but slowly like putty. The comparison is often made to glass or wax. Strike a piece of glass with a hammer and it shatters, hard and brittle. But given enough time, glass can flow very slightly, drooping in the frames of old cathedral windows that have stood for centuries. In the mantle, the time scale is far longer, but the principle is the same. Solid rock, pressed and heated to extremes, shifts in currents, rising and falling like the slow tides of an unseen sea. This movement is called convection. Hot rock deep within the mantle becomes buoyant, rising toward the surface. Cooler rock above sinks downward to take its place. The cycle never ends, a silent circulation that has been running for billions of years. It is these hidden currents that keep the surface alive with change. The drifting of continents is driven by this deep motion. The tectonic plates of the crust, massive slabs that carry oceans and continents alike, ride on the mantle as if on a moving conveyor. They are pushed apart where hot rock wells upward, as at the mid-ocean ridges, and drawn together where cooler material sinks back down. Over tens of millions of years, entire continents are carried across the face of the planet. What seems immovable to us is in fact forever on the move, like rafts drifting on a restless sea of stone. Earthquakes too find their origin in the mantle. When the plates grind, slip, or collide, It is the mantle beneath that supplies the energy. The crust may break, but the force comes from deeper flows, pushing and pulling at its edges. Volcanic eruptions, spilling molten lava onto the surface, are also the mantle's work. The magma we see in eruptions is born when mantle rock melts, rising through cracks in the crust to remind us of the fire that waits below. The mantle is not uniform. Scientists using seismic tomography have mapped places where waves race quickly, suggesting colder and denser rock, and places where waves slow, hinting at hotter, more pliable material. These variations reveal plumes of heat rising from the depths, feeding volcanoes, such as those that form the Hawaiian Islands, and vast slabs of old crust sinking down after being swallowed at the edges of oceans. The mantle records the history of Earth's surface, swallowing fragments of the past and recycling them into new land and new oceans. The scale of time at work in the mantle is almost impossible to imagine. Currents there may take 100 million years to complete a single cycle from top to bottom. Mountains rise, oceans close, and species appear and vanish, all while the mantle continues its slow breathing. It is the hidden rhythm beneath every change we see above. Standing on the surface, it is easy to think of Earth as a stable home, fixed and unchanging. But the mantle reminds us that we live on a restless planet, where rock itself flows and continents drift like leaves on a pond. It is here, in this deep sea of moving stone, that the story of earthquakes, volcanoes, and shifting continents truly begins. For most of human history, the story of water seemed simple. It filled the oceans, fell from the sky as rain, carved rivers across the land, and froze into glaciers that crept down valleys. The water cycle, as it was taught in classrooms, was a surface story. Evaporation, condensation, precipitation, and runoff created a circle that began and ended in the skies and seas we could see. But discoveries in recent decades have revealed that this story is incomplete. Beneath the surface, far below the crust and deep into the mantle, there exists another, hidden chapter of Earth's water. The key to this revelation came not from oceans or lakes, but from tiny crystals. Scientists studying a mineral called ringwoodite uncovered a secret that had been locked away hundreds of miles beneath our feet. Ringwoodite is a rare form of olivine, a mineral that makes up much of the mantle. What makes it remarkable is that it can trap water within its crystal structure. Not liquid water, not ice, but water bound as hydroxide ions tucked inside the lattice of the mineral itself. In 2014, a small fragment of ringwoodite carried to the surface by a volcanic eruption was carefully analyzed in a laboratory. This crystal, no larger than a grain of sand, contained water. Its origin was traced to a depth of roughly 400 miles, within the region scientists call the transition zone of the mantle. That tiny sample was proof that vast amounts of water might be hidden inside the earth, not in oceans or rivers, but locked away in minerals. The implications of this discovery are staggering. If the mantle's transition zone is saturated with ringwoodite, carrying even a modest percentage of water, then the amount trapped there could be immense. Estimates suggest that it may equal, or even exceed, 3 times the volume of all the water in Earth's surface oceans combined. Imagine 3 hidden oceans stacked beneath us, silent and invisible, carried not as free waves or currents, but as molecules held within the structure of solid rock. This unseen reservoir reshapes the way we think about the water cycle. No longer is it just an exchange between sky, land, and sea. Instead, it is a cycle that reaches deep into the mantle, where water can be stored for millions of years before being released again. Subducting tectonic plates, carrying sediments and seawater downward, deliver this water into the mantle. There it becomes bound into minerals, hidden until heat and pressure release it again through volcanic eruptions. In this way, water moves not only across the surface, but also through the vast body of the planet, in cycles that are slower and deeper than anything visible above. The presence of such hidden water may also explain mysteries long debated by geologists. It could influence how easily rocks in the mantle flow, making them softer and more pliable. This, in turn, may affect the movement of tectonic plates and the rise of magma. Water lowers the melting point of rock, meaning regions with more of it could be where volcanic activity is born. It may even play a role in the formation of diamonds, carried upward in eruptions that originate deep within the mantle. There is also a poetic dimension to this discovery. On the surface, we see oceans as the defining feature of Earth, the blue that distinguishes it from every other planet in the solar system. Yet the oceans we sail and study may be only a fraction of the true reservoir. The real water planet may be one whose deepest stores lie in silence, hidden within stone, unseen yet fundamental. This realization forces a shift in perspective. Earth's water is not just a thin skin on the outside, not just a cycle that circles above the ground. It is a substance woven into the very fabric of the planet, part of its deep structure, cycling in and out of minerals, waiting in vast reservoirs no eye has seen. What was once thought of as a surface process is, in truth, an intimate dance between ocean and mantle, between sky and stone. The surface of Earth is restless, its plates drifting like slow rafts across the mantle. Where those plates meet, they collide and grind, sometimes giving rise to mountains, sometimes tearing open deep rifts. In certain places, however, one plate dives beneath another in a process called subduction. It is here that the planet performs one of its most haunting acts, swallowing pieces of its own crust and drawing them down into the depths. For many years, scientists imagined that once a slab of crust descended into the mantle, it would be consumed entirely, melted away, and recycled into new rock. But seismic imaging has shown that this story is far stranger. When scientists listen to the echoes of seismic waves, they find shadows deep in the mantle that match the outlines of subducted plates. These slabs, cold and dense, continue to sink, sometimes plunging hundreds of miles below the surface, their shapes preserved like ghostly fossils inside the living body of the planet. Some of these slabs are astonishingly ancient. They are the remnants of continents and ocean floors that once stretched across the surface, carrying forests, seas, and perhaps entire ecosystems that no longer exist. With time, they were pushed downward by the relentless motion of tectonic plates, sinking into the mantle where they remain entombed. To study them is to glimpse the bones of worlds long vanished, sealed away in stone far below our feet. The scale of this burial is immense. Imagine a section of ocean floor, thousands of miles long and miles thick, forced beneath another plate and slowly carried downward. The weight of such a slab is unimaginable, yet the mantle takes it in, folding it into its slow circulation. Some of these slabs are still sinking today, descending into darkness mile by mile. Others, pushed deep in the distant past, may lie near the core-mantle boundary, preserved for hundreds of millions of years. These buried pieces of crust are more than geological curiosities. They shape the behavior of the mantle itself. Being colder and denser than the surrounding rock, they can slow down or redirect the great currents of convection. They may even be responsible for regions of unusual seismic activity, where stresses build as the slabs twist and deform. In some cases, their presence deep below may help to trigger volcanic chains at the surface as melting rock rises from the distorted boundaries between slab and mantle. There is a kind of poetry in the idea that Earth eats itself. The surface, fragile and thin, is constantly broken apart and drawn downward, consumed into the mantle, yet never fully erased. Ghost continents slumber far below, fragments of ancient geography that once shaped the surface world but are now hidden in silence. In this way, the planet holds onto its history not only in the layers of rock we can touch, but also in the invisible structures preserved deep inside. One striking example comes from the Pacific Ocean, where vast slabs of former ocean floor have been traced sinking toward the lower mantle. These are relics of subduction zones that existed tens of millions of years ago, when the arrangement of continents and oceans was very different from today. They now lie like sheets of shadow, detected only by the way seismic waves slow as they pass through. Elsewhere, beneath North America and Eurasia, similar ghostly slabs tell the story of ancient collisions that reshaped the continents above. Even more haunting is the possibility that some of the slabs may never fully dissolve. If they reach the base of the mantle, near the boundary with the outer core, they may linger for geologic ages, a graveyard of swallowed crust resting against the fiery ocean of molten iron below. Some scientists believe that the mysterious regions of unusual density found at that boundary, known as ultra-low velocity zones, may be formed in part from these ancient slabs. If so, the deepest parts of Earth contain not only the memory of the surface, but also its remains, preserved in silence. This cycle of destruction and preservation is one of the forces that makes Earth unique. The crust does not simply sit still, as it does on Mars or the Moon. Instead, it is broken, swallowed, and reborn in an endless rhythm. Life itself has been shaped by this hidden recycling, as continents shift and oceans open and close, driven by the burial and return of crust. Every tremor, every eruption, and every drifting continent is linked to this hidden dance. Ghost continents lie beneath us, waiting in darkness, their shapes etched into the mantle. They remind us that the surface world is temporary, forever changing, while deep inside, the planet keeps the shadows of its past. Deep beneath the mantle, near the place where rock meets the molten sea of the outer core, scientists have discovered something strange. When seismic waves pass through most of the mantle, they travel at predictable speeds, bending and curving as expected. But at certain depths, those same waves suddenly slow to a crawl, as if they had struck something heavy and alien. These mysterious patches are called ultra-low velocity zones, and they represent one of the deepest puzzles inside our planet. The very existence of these zones was uncovered through the careful study of seismic echoes. Earthquakes send ripples in every direction, and when those ripples encounter boundaries between different materials, some of the energy reflects, while the rest continues onward. By collecting these faint echoes with sensitive seismometers, scientists can reconstruct the shapes and properties of hidden structures thousands of miles down. What they found at the base of the mantle was unlike anything they had expected. Instead of a smooth transition from rock to molten metal, the seismic signals revealed scattered regions where waves slowed dramatically, up to 10 times more than usual. These zones are not small. Some are hundreds of miles wide and tens of miles thick. They sit like colossal, irregular blobs on the boundary between mantle and core, patches of unusual density and composition resting in one of the inaccessible inaccessible places on Earth. What exactly they are remains uncertain. One possibility is that they are formed from piles of ancient crust, slabs of ocean floor that sank during subduction and never fully melted. Over millions of years, these slabs could have accumulated at the base of the mantle, forming strange, dense provinces that still linger today. If so, they are the final resting place of Earth's recycled skin, hidden miles beneath the surface in a graveyard of lost worlds. Another, more dramatic possibility is that these zones are not entirely of earthly origin. Billions of years ago, in the violent days of the early solar system, a planet sized body known as Theia is believed to have collided with Earth. The impact was catastrophic, blasting molten debris into orbit that later coalesced to form the Moon. But the collision may not have ended there. Some scientists suggest that parts of Theia's mantle sank deep into Earth, merging with our own interior. If this is true, then the ultra-low velocity zones could be the preserved remains of that long vanished world, a foreign planet buried inside our own. The idea is haunting, that Earth carries within it the bones of another planet, fragments of an ancient body resting just above the core. The moon we see in the night sky may be the outward reminder of that collision, but deep below, the silent remnants may still exist, fused into the hidden architecture of our planet. What gives weight to this theory is the density of the zones themselves. Seismic studies suggest they are made of material much heavier than the surrounding mantle, consistent with the idea of alien rock merging with Earth. Some of the zones also seem to align with hotspots at the surface, such as Hawaii and Iceland, where plumes of magma rise from deep within the mantle. It is possible that these buried remnants are not only silent witnesses of the past, but active participants in shaping the present, feeding volcanic activity at the surface. The mystery of the ultra-low velocity zones highlights just how little we know about the depths of our planet. They could be piles of Earth's own crust, swallowed and preserved. They could be pieces of Theia, a hidden legacy of a cosmic collision. Or they could be something else entirely, a form of matter not yet fully understood, waiting in the deepest dark where no drill or probe can ever reach. What is certain is that these zones remind us of the planet's complexity. Far from being uniform, the mantle hides strange provinces that defy simple explanation. To imagine them is to picture vast, dense masses lurking at the edge of the core, ancient and silent, shaping the planet from within. They are ghostly continents of stone, some born of earth, others perhaps born of a different world, all hidden in the unseen depths. Beneath the mantle, past the fractured crust and the strange hidden blobs at the boundary, lies a realm unlike anything on the surface of Earth. This is the outer core, a vast sea of molten metal that begins roughly 1,800 miles beneath our feet and extends to about 3,200 miles down. It is here that solid rock finally gives way, replaced by a liquid ocean of iron and nickel, heated to unimaginable temperatures. The outer core is one of the most alien places within the planet. The pressures are immense, and the temperatures rise to nearly 6,000 degrees Celsius, almost as hot as the visible surface of the sun. At such extremes, metals that would normally be hard and unyielding on the surface of the Earth behave very differently. They melt into a glowing fluid, moving and swirling in slow, powerful currents. This metallic sea is in constant motion, driven by heat rising from the deeper interior and by the slow cooling of the core itself. Scientists imagine it as a restless ocean of fire, waves of molten iron rolling and colliding in cycles that can last thousands of years. These flows are not random, they follow patterns shaped by heat, pressure, and rotation. As Earth spins on its axis, the liquid metal within the outer core is set into spiraling motion, twisting into great currents that circle the globe from within. It is from this hidden ocean that one of Earth's most vital protections arises. The movement of molten iron and nickel generates electric currents. These currents, in turn, produce a magnetic field that extends far beyond the surface of the planet. This invisible shield stretches outward into space, deflecting the constant stream of charged particles pouring from the sun. Without it, the solar wind would strip away the atmosphere in a matter of time, leaving Earth as bare and exposed as Mars. The outer core acts like a planetary dynamo, a self sustaining engine that has been running for billions of years. Even though we can never visit it directly, its effects can be measured all around us. Compasses point north because of the magnetic field born in this fiery ocean. Auroras shimmer in the polar skies when charged solar particles collide with the edges of the field. The fact that we can breathe, that oceans remain, and that life thrives on the surface is possible because of the shield that rises from this restless sea of molten metal. The discovery of the outer core was itself an extraordinary act of listening. Scientists notice that certain kinds of seismic waves vanish when they try to pass through this region. Secondary waves, which cannot travel through liquid, are stopped at the boundary, while primary waves slow down, bent by the change from solid mantle to liquid core. From these patterns, seismologists deduced that Earth must contain a vast layer of molten metal. Later studies confirmed not only its size and depth, but also the fact that its swirling motion gives rise to the magnetic field. Within the outer core, the story of Earth continues to unfold. The cooling of this molten layer releases heat upward into the mantle, fueling the convection that drives plate tectonics on the surface. At the same time, parts of the outer core slowly solidify, adding to the inner core and releasing additional energy that keeps the magnetic dynamo alive. The outer core is both a shield and an engine, connecting the hidden depths of the planet to the landscapes we see above. This immense ocean of molten iron is unlike anything that exists on the surface. There are no landmarks, no coastlines, no sky above it, only a churning sea of fire stretching for thousands of miles around the planet, endlessly flowing in patterns we can scarcely imagine. Though hidden, its influence reaches into every part of our lives, shaping the air we breathe and the stability of our world. Far above the surface of Earth, beyond the clouds and the blue sky, space is not empty or still. It is filled with a constant wind, a stream of charged particles flowing outward from the sun at incredible speeds. This solar wind races across the solar system, bombarding planets, stripping atmospheres, and carrying with it the raw energy of a star. For most worlds, this relentless storm is devastating, but Earth is different. Around our planet, there exists an invisible shield, a magnetic field born deep within the molten heart of the outer core. The source of this shield lies nearly 2,000 miles beneath our feet, in the churning ocean of liquid iron and nickel. As this molten metal moves and spirals in response to heat and planetary rotation, it generates powerful electrical currents. Those currents create a magnetic field, and as the flows continue, the field sustains itself in a feedback loop known as the geodynamo. Though hidden in darkness, this restless sea of fire keeps an invisible barrier wrapped around the planet, stretching tens of thousands of miles into space. The importance of this shield cannot be overstated. Without it, Earth would be vulnerable to the full force of the solar wind. Charged particles from the sun would collide directly with our upper atmosphere, gradually blasting it away. Mars offers a sobering example. Billions of years ago, Mars likely had rivers, lakes, and perhaps even oceans, but when its smaller core cooled and its magnetic field faded, the solar wind stripped its atmosphere over time, leaving behind the barren desert world we see today. On Earth, the magnetic field has preserved our air, our water, and the fragile conditions that allow life to flourish. The shield does more than protect. It also interacts with the particles it deflects, channeling them along the magnetic poles. When these particles collide with atoms in the upper atmosphere, they release energy in glowing curtains of green, red, and violet light. These are the auroras, shimmering displays that dance in polar skies, silent reminders of the vast energies moving invisibly above our heads. The beauty of the aurora is the visible face of a hidden guardian, proof that the magnetic field is working tirelessly to protect us. The story of Earth's magnetic field is written not only in the skies, but also in stone. As lava cools and hardens, the iron minerals within align with the magnetic field, like tiny compass needles frozen in place. These rocks record the direction and strength of the field at the time they formed. By studying such records, scientists have uncovered an astonishing truth. Earth's magnetic poles have not always been fixed. Throughout history, the poles have reversed many times. North has become south, and south has become north, in a pattern of magnetic flip-flops stretching back hundreds of millions of years. These reversals do not happen on a human timescale. They unfold over thousands of years, so slowly that life on the surface has continued largely unaffected. Yet the rock record reveals that the magnetic field is not a permanent fixture. It shifts, it wavers, it strengthens, and it weakens, all in response to the flows of molten iron deep in the outer core. This constant movement is a reminder that the shield we depend on is alive, changing as the planet itself evolves. Even today, satellites orbiting Earth measure the magnetic field with precision, and they show that the field is not uniform. In some regions, it is stronger, in others, weaker, and there are zones like the South Atlantic anomaly where radiation dips closer to the surface than elsewhere. These subtle irregularities are natural, but they reveal that the shield is dynamic, forever shifting as the ocean of fire beneath us moves. Without this protective field, Earth would be a very different world. The oceans might have been stripped away long ago. The air would have thinned until breathing was impossible. Life, if it arose at all, would face constant bombardment from solar and cosmic radiation. The conditions that make our world blue and green, alive with forests and oceans and creatures of every kind, would never have been sustained. The magnetic shield is invisible, yet its presence shapes everything we know. It is the quiet guardian of life, born from the restless metal currents of the outer core, stretching outward to meet the solar wind, deflecting danger while letting life thrive in the calm below. Far below the restless ocean of molten iron in the outer core, the journey continues deeper still. About 3,200 miles beneath the surface, there lies something even more astonishing. Here, at the very heart of the planet, is a sphere of iron and nickel, a world within a world. It is called the inner core, and though hidden from all eyes, it is one of the most extraordinary realms on Earth. The inner core is solid, though everything around it is liquid. Its diameter stretches for more than 700 miles, making it nearly the size of the moon. It is made mostly of iron, with nickel and small amounts of lighter elements mixed in. This sphere is the densest place on Earth, so compact that a single teaspoon of its material would weigh as much as a mountain boulder. Yet what makes it truly remarkable is not only its size or its density, but the fact that it exists at all in such conditions. The temperatures here rise to more than 10,000 degrees Fahrenheit, hotter than the visible surface of the sun. By all ordinary rules, iron at this heat should not be solid. It should glow and flow like the molten metal above it. But in the inner core, another force takes command. The pressure at these depths is unimaginable, more than 3.5 million times the air pressure we feel at sea level. Under such crushing weight, atoms cannot move freely. Even with the searing heat trying to force them apart, they are pressed together so tightly that they lock into place. The result is a paradox, iron that is both unimaginably hot and yet solid, forged by the immense gravity of the planet itself. This balance between heat and pressure is delicate, like a cosmic stalemate. Without the crushing weight of the overlying layers, the inner core would melt instantly. Without the heat, the atoms would remain frozen and immobile. Instead, the two forces meet here at the center of the Earth and create something unique, a blazing solid heart at the center of a world alive with fire and motion. The inner core is not just a static lump of iron. Seismic studies suggest it has texture and structure of its own. Waves passing through it hint that crystals of iron inside are aligned in particular directions, like fibers running through a piece of wood. This alignment gives scientists clues about the way the core is growing and evolving. In recent years, evidence has even pointed to the possibility that the very innermost part of the core, a region sometimes called the inner core, might be subtly different again, with crystals oriented in another way. It suggests that Earth's heart is layered, a record of the planet's deep history etched in iron. The discovery of the solid inner core in the early 20th century was a revelation. Before then, scientists thought the center of the Earth might be fully molten, but as seismographs improved, researchers noticed something unexpected. Certain earthquake waves could pass through the center in ways that did not fit a liquid interior. Only a solid could explain the pattern. The finding transformed our picture of the planet, showing that Earth was not simply a ball of rock and fire, but a complex body with a hidden structure as intricate as any organism. The existence of this solid heart also plays a role in the life of the planet as a whole. As the inner core slowly crystallizes, it releases heat into the outer core, helping to drive the swirling flows that sustain the magnetic field. In this way, the inner core is not only a passenger at the center of Earth, but a participant in its story, quietly feeding the dynamo that shields the surface from solar storms. Without this interaction, the magnetic field might be weaker or less stable, leaving our world more vulnerable to the harshness of space. Even though no probe will ever reach this far, every earthquake continues to send whispers through the deep, carrying messages about this blazing sphere. From those ripples, scientists piece together the outlines of a place where matter exists under conditions unlike anywhere else on Earth. The inner core reminds us that beneath the familiar landscapes of oceans, forests, and mountains lies a realm stranger than imagination, where heat and pressure combine to form a solid heart that burns hotter than the stars we see at night. For most of the 20th century, it seemed as though the great mystery of Earth's interior had been settled. The crust and mantle, the molten outer core, and the solid inner core were like the nested shells of a cosmic fruit. The picture was elegant, and for a time it seemed complete. But as scientists kept listening more closely to the faint vibrations that earthquakes send through the planet, they began to notice subtle patterns that did not quite fit. It was as though the inner core itself was hiding another secret, a deeper heart within the heart. By the start of the 21st century, evidence began to build for something extraordinary, a second inner sphere buried inside the first. This innermost zone, sometimes called the inner core, is smaller than the one surrounding it, yet it may hold clues to the deepest story of our planet. The discovery did not come from digging or drilling, for no tool could ever reach so far. It came from the delicate art of seismic analysis, the practice of decoding how earthquake waves travel through different materials. These waves are like invisible messengers. They race across the surface, dive into the mantle, slip through the molten outer core, and even pierce the solid inner core. By comparing how quickly they move and in what directions they bend, scientists can infer the shapes and properties of the hidden layers. When these signals were studied in fine detail, something unusual was revealed. The waves moving through the very center of Earth behaved differently from those passing through the surrounding inner core. It was as if the iron crystals in this deepest region were aligned in a new direction, distinct from the orientation in the layers around them. This subtle shift in texture suggested that the planet's heart was not uniform, but had at least two separate phases in its history. Imagine a tree trunk sliced open, its rings marking the passage of time. In a similar way, the inner core may represent a fossilized record of Earth's earliest days, a place where the first crystals of iron locked together under impossible pressures. Later, as the outer layers of the inner core grew, the alignment of the crystals changed, leaving behind a layered signature that still whispers through earthquake waves. This idea transforms the way we think about the planet's formation. The existence of a distinct inner core hints at a turning point in Earth's evolution, perhaps a moment when conditions in the core shifted dramatically. It might have been triggered by changes in temperature, or by the slow cooling of the outer liquid layers, or even by the chemistry of elements mixing deep below. Whatever the cause, the fingerprints of that transition remain frozen in iron, thousands of miles beneath our feet. Though this realm is unimaginably remote, its significance stretches outward to touch every part of our lives. The way the core solidifies, layer by layer, affects the flow of heat through the outer liquid metal, which in turn drives the magnetic field. That shield, invisible but essential, is the reason our atmosphere remains thick and protective. The inner core, small though it may be compared to the whole Earth, might be a key piece in the story of why our planet has endured when so many others in the solar system grew silent. There is also poetry in the discovery. At the center of the Earth, beneath thousands of miles of rock and fire, lies a hidden world inside another hidden world. It is a reminder that even in the places we think we understand, nature holds deeper layers of mystery. Each advance in science opens a door, only to reveal another door waiting beyond it. The inner core is not something we can see or touch, yet its presence changes the way we imagine the planet. It reminds us that Earth's heart is not a simple sphere of iron, but a living archive, recording billions of years of cosmic history. Seismic waves, rippling from the fractures of earthquakes, are the only reason we know it exists. Without them, this world within a world would remain forever invisible, its story untold. The deeper we journey into Earth's interior, the more familiar ideas begin to fall apart. Gravity presses downward from every direction, and with each mile closer to the center, the weight of everything above grows heavier. By the time we reach the core, the pressure has risen to a level that words can hardly hold. Scientists estimate it at roughly 3.5 million atmospheres. To place that into perspective, one atmosphere is the gentle weight of air at sea level, pressing on every inch of your skin. Imagine that multiplied not by hundreds, not by thousands, but by millions. It is a crushing force beyond anything we can reproduce on the surface for more than a fleeting instant. Under such pressure, matter itself takes on strange and unfamiliar forms. Iron, which we know on the surface as a hard, solid metal, is transformed. In the outer core, where it is molten, this weight still bears down so powerfully that the liquid iron moves not like water, but with a heaviness more like honey. Even in its molten state, it resists, dense and sluggish, sliding in slow, powerful currents that shape the planet's magnetic field. In the inner core, iron and nickel are locked into a solid despite the searing heat, which climbs higher than the visible surface of the sun. Pressure has overruled temperature, forcing atoms into tightly packed arrangements that cannot break free to flow. Rocks, too, behave in ways that seem contradictory. On the surface, stone is brittle. Drop it, and it cracks. Heat it, and it crumbles. But under the immense weight inside the earth, rock can flow. It bends and stretches, not in minutes or hours, but over spans of millions of years. To human eyes, it would appear still, yet given enough time, it behaves like a slow moving fluid, creeping in grand currents that carry continents above it. What we call solid ground is built on these moving foundations. The physics here bends into something almost poetic. At 3.5 million atmospheres, the lines that divide solid from liquid, rigid from soft, are blurred. Matter seems to exist in states that defy the tidy categories we learn in school. Iron can be both solid and yet quivering with vibrations, as if it were fluid. Rock can be both firm and yet flowing. The planet's heart is a realm where definitions fail, and imagination must take their place. To explore these extremes, scientists recreate fragments of the core's conditions in the laboratory. They use diamond anvil cells, devices that press tiny samples of material between the hardest crystals on Earth until pressures climb to millions of atmospheres. Lasers then heat the samples to thousands of degrees, imitating the inferno of the core. Even in these controlled experiments, matter behaves in ways that surprise us. Atoms rearrange themselves into exotic forms, bonds break and reform, and structures emerge that exist nowhere else in the natural world. Each discovery is like a whispered clue from the deep, reminding us how alien the familiar elements can become when forced into such unimaginable conditions. If we think of the Earth as a great living organism, then pressure is its heartbeat. It drives the dynamics that keep the core spinning, the mantle flowing, and the crust shifting. It is invisible, silent, and relentless. Without it, the inner core could not remain solid. Without it, the great convection currents of the mantle would not churn. Without it, the magnetic shield that defends us from the fury of the sun would not exist. The sheer scale of these forces invites metaphors, for ordinary words stumble when faced with millions of atmospheres. One might picture the weight of entire mountain ranges stacked overhead, multiplied again and again until steel itself would crumple like paper. Or think of a cathedral of pressure so vast that it holds back a sea of molten fire, shaping it, restraining it, forcing it into patterns that ripple outward and touch every breath of air we take on the surface. It is pressure that holds the earth together and pressure that allows it to live. At the very center, where iron is compressed into crystalline structures and where rocks behave like fluids, physics becomes poetry. The ordinary laws still apply, but they are stretched and bent in ways that feel almost otherworldly. It is a reminder that the universe is not bound by what feels intuitive to us. Beneath our feet lies a realm where atoms dance under impossible weights, where matter bends but does not break, where silence is filled with crushing force. Deep beneath the mantle and the sea of molten iron, within the blazing inner sphere of iron and nickel, something remarkable is happening. The inner core does not sit quietly at the planet's center like a fixed stone. It moves, not in the way continents drift or oceans rise, but with a hidden rhythm of its own. Evidence suggests that this solid inner sphere rotates differently than the surface of the Earth above it. It is as though the heart of the planet turns to its own quiet tempo, drifting slightly out of step with the crust, the mantle, and the world we know. Scientists first began to suspect this strange motion by listening to the echoes of earthquakes. Seismic waves travel through the planet in ways that reveal subtle differences, and by comparing tremors recorded decades apart, researchers noticed that the inner core's signals seemed to shift. These small changes hinted at something extraordinary. The inner core itself might be spinning at a slightly different rate than the rest of Earth. For a time, it was thought that the inner core turned just a little faster, completing one extra rotation every few hundred years. Later studies showed the picture might be more complex. At times, the core seems to move ahead. At other times, it lags behind. Its motion is not fixed but appears to oscillate, like a pendulum swinging slowly back and forth over the course of decades. Imagine Earth as a set of nested spheres, each one turning in relation to the others. The crust and mantle move together, carrying continents and seas. The liquid outer core churns in restless currents, generating the magnetic field, and at the very center, the inner core rotates with a subtle independence, sometimes faster, sometimes slower, as if listening to a deeper rhythm. The forces behind this slow spin are tied to the tug of war between gravity and magnetism. The mantle and crust exert their own pull, while the flowing metal of the outer core creates magnetic forces that can nudge the inner sphere. Locked inside this balance, the inner core shifts its pace, carried forward by unseen currents, and restrained again by the immense weight pressing down from above. This slow and irregular rotation is not just an odd curiosity, it may ripple outward in ways that touch the surface of our lives. Some studies suggest that tiny changes in the length of Earth's day could be linked to the inner core's shifting pace. The difference is incredibly small, measured in fractions of a second, yet over time, even such subtle variations remind us that the stability we take for granted is balanced on hidden motions beneath our feet. The thought is both unsettling and comforting. The ground we walk on feels solid and unchanging, yet deep below, the very heart of the planet turns on its own schedule. It is like a secret clock, ticking slowly in a dark chamber we cannot see. The surface world of oceans, mountains, and skies is tied in quiet ways to this hidden rhythm. Our ability to uncover such a secret is itself a marvel. No probe has reached the core, no machine has come close. Everything we know about this slow spin comes from listening with patience, comparing the subtle signatures of waves that traveled through Earth decades apart. The planet whispers through tremors and quakes, and in those whispers, scientists have found signs of a heart that does not keep perfect time. In this strange and hidden motion lies a reminder of Earth's complexity. The core is not static, but alive with subtle movement. Its spin may shift by only the smallest measure, yet that shift hints at the deep connection between the blazing interior and the quiet surface where life unfolds. The core, wrapped in crushing pressure and searing heat, does not merely exist at the center of Earth. It breathes, it moves, and in its motion we glimpse a planet that is never still, even in its deepest heart. At the very center of the planet, in a place no light has ever touched, the inner core is slowly changing. Although it seems locked in timeless stillness, scientists now understand that it is not frozen in eternity, but quietly growing. With every passing moment, tiny structures of iron crystallize out of the molten metal surrounding them, adding layer upon layer to the solid heart of Earth. It is a process that has been unfolding for billions of years and will continue for billions more. This growth happens because the outer core, the sea of liquid iron and nickel that surrounds the solid center, is cooling little by little. Cooling is not something we notice on the surface, for the mantle and crust hold the heat tightly inside, but over the vast expanse of geological time, energy slowly seeps away into space. As it does, the molten outer core loses just enough heat for iron to solidify at the very center, where pressures are highest. Each newly formed crystal joins the growing inner sphere, marking another heartbeat in the hidden life of the planet. The process is not simple freezing. When iron crystallizes, it releases latent heat, a form of stored energy. This released heat is not wasted. It rises into the liquid outer core, stirring it into motion. That motion keeps the great convection currents alive, which in turn helps sustain the magnetic field that shields our world from the sun. In this way, the growing heart of Earth is not only a solidifying core, but also a source of energy that reaches far beyond itself. In addition to heat, crystallization squeezes out light elements such as sulfur and oxygen from the solid iron, leaving them to mix into the outer core. These lighter elements rise through the molten metal, adding more currents and swirls to the restless ocean of liquid iron. The inner core's slow growth thus creates both the heat and the chemical push needed to keep the dynamo of the outer core churning. Without this constant stirring, the magnetic shield around Earth could fade. The very survival of life on the surface depends, in part, on this invisible growth taking place 3,000 miles below. To imagine the rhythm of this process, picture iron atoms lining up and locking together into crystals under pressures so great they crush matter into unfamiliar forms. These crystals grow outward, one upon another, expanding the sphere in a steady pulse. Some scientists have even described this as a kind of planetary heartbeat, not in seconds or minutes, but in the slow tempo of geological time. The heart of Earth beats in the growth of iron, silently and invisibly, and through it the planet is kept alive. The speed of this growth is astonishingly slow by human standards, yet immense when viewed across ages. Each year, the inner core grows by only a fraction of a millimeter. Over millions of years, this amounts to miles of solid iron added to the planet's center. It is a reminder of how time stretches differently in geology. What seems motionless to us is revealed, through careful study, as a grand unfolding in which every second plays a role. The discovery of this growth came from seismic studies. Waves from distant earthquakes pass differently through various regions of the inner core, hinting at the way crystals are arranged. Some areas seem older, built of iron that crystallized long ago, while others appear younger, still forming in the present. This suggests that the growth may not be even. Instead, one side of the inner core may grow more quickly than the other, tilting the balance slightly and leaving scientists with fresh mysteries about how this process unfolds. The implications ripple outward. The growth of the inner core is not simply an isolated event. It connects to the outer core's flow, to the magnetic field, to the shield that preserves the air we breathe, and to the climate stability that allowed life to flourish. Each aligned iron crystal at the center of Earth becomes part of a chain of consequences that stretches to the farthest edges of the atmosphere. The hidden growth deep below is woven into the daily experience of life on the surface. The growing heart of Earth is one of the most delicate and powerful processes in nature. It is not loud or sudden like an earthquake, nor is it spectacular like a volcanic eruption. It is patient, steady, and unseen, yet its influence spans the globe. The slow crystallization of iron is a quiet engine pulsing at the center of our world, binding together the fate of the deep and the fate of life above. Far beneath the crust, beyond the mantle and into the hidden fires of the core, something invisible is being born every moment. Tiny subatomic particles slip into existence as radioactive elements decay deep within Earth's interior. These particles are called geoneutrinos, and though they are unimaginably small and elusive, they carry whispers of the planet's secret furnace. Radioactive decay is one of the quiet engines that powers Earth. Elements such as uranium, thorium, and potassium are buried in the rocks of the mantle and crust. As their atoms break apart over time, they release heat that rises upward, keeping the mantle in motion and the outer core alive with swirling currents. Along with this heat comes a stream of nearly massless particles, so faint and insubstantial that trillions pass through your body every second without leaving a trace. These are the geoneutrinos, ghosts of the deep, born in silence but carrying messages about the inner life of the planet. For decades, their existence was predicted but never confirmed. Neutrinos in general are notoriously difficult to catch. They hardly interact with matter, slipping through entire planets as if nothing were there. To detect even a handful, scientists must build vast underground observatories shielded from the background noise of cosmic rays. Inside, these observatories are enormous tanks filled with clear liquid scintillators, or water, instruments so sensitive they can record the faint flashes of light produced when a passing neutrino collides with an atom. It was in such observatories that the first geoneutrinos were finally detected. The Camland experiment in Japan, buried under mountains for protection, recorded signals in 2005 that revealed the presence of geoneutrinos rising from Earth itself. Later, the Borexino detector in Italy confirmed the finding, showing that these elusive particles were indeed flowing outward from radioactive decay inside our planet. For the first time, humanity had a direct way of measuring the hidden fires that have burned for billions of years. The discovery was more than a technical triumph. It opened a new window into the story of Earth's heat. Until then, scientists could only estimate how much of the planet's internal warmth came from its birth when gravity squeezed matter into a molten sphere, and how much came from ongoing radioactive decay. With geoneutrino data, those guesses could be tested. The measurements revealed that a significant portion of Earth's heat, perhaps nearly half, still comes from the steady breakdown of radioactive elements locked deep inside. The core is not only cooling but also fueled from within, kept alive by atoms crumbling in silence. To imagine geoneutrinos is to think of particles without weight or form, drifting endlessly through space and matter. They are not bound by walls or oceans or skies. They pass through mountains, through your body, and through the entire Earth almost without slowing. Yet, with enough patience and instruments vast enough, scientists can listen for them, catching rare flashes that tell of events occurring thousands of miles below. Each geoneutrino that is detected is a messenger from the deep, proof that radioactive furnaces continue to burn inside the Earth. There is a strange comfort in this knowledge. Though the surface is shaped by storms, earthquakes, and shifting climates, deep inside the planet, a steady process continues with patient regularity. Atoms decay, heat is released, geoneutrinos are born, and the planet's inner fire is kept alive. The currents of the outer core, the movement of continents, even the shimmering auroras at the poles, are all in some way tied to this invisible work of particles too small to see. The study of geoneutrinos is still in its beginning. Future observatories may measure them more precisely, mapping how radioactive elements are spread through the mantle and core. With that knowledge, we may better understand the balance of forces that keeps Earth geologically alive, while other planets like Mars grew still and silent. For now, the few faint signals already tell a profound story that Earth is not a cold stone drifting in space, but a living world warmed by the decay of ancient atoms, with ghostly particles as its quiet witnesses. Among all the treasures pulled from beneath the Earth, few capture the imagination like diamonds. Their brilliance on the surface hides a far greater story, one that begins not in jewelry boxes or mine shafts, but in the crushing depths of the mantle. A diamond's journey starts more than 100 miles below the crust, in a place where carbon is forced into its hardest and most enduring form. In those depths, the conditions are unlike anything we know above. Temperatures soar to thousands of degrees, and pressures climb to levels that would crush any ordinary mineral. Carbon, which on the surface can take the form of graphite or coal, is transformed here into something extraordinary. Its atoms lock together in a tight, repeating pattern, creating a crystal so strong it can outlast nearly anything. This crystal is what we know as a diamond, though in the dark mantle it has no sparkle, no shine. It is only when carried upward and revealed at the surface that its true brilliance appears. The ascent of a diamond is just as remarkable as its birth. They are not lifted gently, but hurled toward the surface in violent eruptions that tear through the mantle. These eruptions form rare volcanic structures called kimberlite pipes, channels that serve as elevators from the unseen world below. Without such eruptions, diamonds would remain forever trapped in silence, hidden away in the depths of the planet. Each stone that reaches us is a survivor of both crushing pressure and explosive release. What makes diamonds so precious to scientists is not just their beauty but their role as messengers. Some carry within them tiny inclusions, microscopic flecks of minerals that were trapped inside as the crystal grew. These inclusions are more valuable for knowledge than the diamond itself. They are physical samples of the deep earth, pieces of the mantle preserved and delivered to the surface. In some cases, these inclusions have revealed minerals that could not survive in ordinary conditions, existing only under the colossal pressures of the mantle. One such discovery was ringwoodite, a form of mineral that holds water within its crystal structure. For years, its existence in the mantle was only predicted through experiments and seismic studies. Then, a single diamond was found to contain a speck of ringwoodite, providing the first direct evidence that vast amounts of water may be hidden hundreds of miles below our feet. In this way, a tiny inclusion inside a gem reshaped our understanding of the Earth's water cycle, suggesting that subterranean reservoirs could rival the oceans on the surface. Other diamonds have carried signs of carbon cycling deep into the planet, revealing how surface material can be drawn down through subduction zones, transformed, and then re-emerge locked inside crystal. These time capsules show that the Earth's surface and interior are not separate realms but part of one connected system, endlessly exchanging matter through slow and powerful processes. The age of diamonds also adds to their story. Some are thought to be more than 3 billion years old, older than many of the continents, and almost as ancient as the planet's earliest life. Holding such a stone is like holding a relic of Earth's infancy, a record of conditions long vanished. It is not just a gem, but a page in the diary of the planet, written in the language of atoms and pressure. Even the imperfections of diamonds are meaningful. While flawless stones are prized in jewelry, it is the flawed ones, riddled with inclusions and irregularities, that scientists most cherish. Each imperfection is a clue, a fingerprint left by the deep earth. Studying them with powerful microscopes and lasers allows researchers to reconstruct the hidden environments where they formed. Diamonds remind us that beauty on the surface is only a shadow of the stories written in the depths. They are not merely ornaments, but windows into a world we cannot otherwise touch. With each diamond that comes to light, we are offered a glimpse of the mantle's secret workshop, where carbon is pressed into crystal and the memory of deep earth is locked away for ages. The surface of Earth feels like a world of its own, filled with air, oceans, forests, and life. Yet, its stability is tied to hidden cycles that reach far beneath our feet, into regions no human hand will ever touch. Two of the most important players in this underground story are carbon and water, locked deep within the mantle and moving through the planet in ways that quietly shape the surface we know. Carbon is the foundation of life, the backbone of every plant, animal, and human. On the surface, it flows visibly through the atmosphere and oceans, traded between forests, seas, and living creatures. But a much larger and older reservoir lies hidden below. Deep within the mantle, carbon is stored in minerals that form under crushing pressures. It is carried downward when tectonic plates slide beneath one another, pulling pieces of the ocean floor and carbon-rich sediments into the mantle. There, carbon may remain trapped for millions of years, locked in crystal lattices far beneath the crust. Eventually, some of this deep carbon makes its way back to the surface. It rises in plumes of magma, escapes through vents, and erupts from volcanoes as carbon dioxide. Every volcanic plume we see is part of a cycle that stretches across thousands of miles and millions of years. The air we breathe today carries traces of carbon that once rested in the mantle, reminding us that even the atmosphere is linked to the hidden heart of Earth. Water, too, has its secret paths beneath the surface. For centuries, people thought of the oceans as the total storehouse of Earth's water. Yet discoveries of minerals like ringwoodite, capable of holding water within their structures, revealed another truth. Water cycles extend far deeper than the surface seas, plunging hundreds of miles into the mantle. As oceanic crust is pulled downward at subduction zones, it carries hydrated minerals with it. These minerals lock away water molecules, holding them tight under extreme heat and pressure. At great depths, this water may be released again, fueling volcanic activity and creating plumes of magma that rise upward. In this way, water is recycled through the planet, circulating invisibly between the oceans, crust, and mantle. The deep water cycle is not separate from life on the surface, but intricately bound to it. The eruptions it feeds shape landscapes, enrich soils, and influence the very climate that sustains ecosystems. The deep carbon cycle and the deep water cycle are not independent stories. They intertwine, feeding into one another and balancing the planet's systems. Water carried deep into the mantle can lower the melting point of rocks, releasing stored carbon. Carbon rising with magma can change how water is released, fueling eruptions with explosive force. These exchanges are delicate and continuous, shaping not only the geology of Earth, but also its ability to host life. What makes these cycles so extraordinary is their timescale. On the surface, we measure seasons, years, and centuries. Beneath, the exchanges of carbon and water take place across millions of years. A drop of water carried into the mantle by a sinking plate may not return to the surface until long after continents have shifted and entire species have come and gone. A fragment of carbon trapped in a mineral may rest for ages before it rises again in a volcanic exhalation. These are cycles that move not with the pace of human life, but with the rhythm of the earth itself. And yet, though they move in silence, their influence is everywhere. Without the deep water cycle, volcanoes would erupt differently, mountain ranges might not rise, and the landscapes we inhabit would be reshaped. Without the deep carbon cycle, the atmosphere could collapse into instability, either starved of carbon dioxide or overwhelmed by it. Life as we know it depends on these unseen exchanges flowing steadily between the mantle and the surface. It is humbling to realize that each breath carries a trace of these hidden processes. The air is not just a gift of forests and seas, but also of fire and stone from the deep earth. Each glass of water is not only drawn from rivers and clouds, but is connected, in ways invisible to the eye, to reservoirs locked hundreds of miles below. The deep cycles of carbon and water are not distant mysteries. They are the quiet foundations of life itself, tying every heartbeat and every breath to a world that stretches thousands of miles beneath our feet. Long before forests spread across continents, before fish filled the seas or birds filled the skies, Earth was a barren and hostile place. The young planet had oceans, but no living creatures swam in them. The surface was bombarded by comets and meteors. The air was heavy with gases, and sunlight alone may not have been enough to spark the chemistry needed for life. Instead, scientists believe the first sparks may have come from deep within, from the hidden energy rising out of the planet's core. This energy revealed itself most dramatically at hydrothermal vents, fissures on the ocean floor where seawater seeps down into cracks, is heated by magma, and then bursts back upward in towering plumes. These vents are not gentle trickles. They roar like underwater geysers, pouring out mineral-rich water at temperatures that can exceed hundreds of degrees. Around them, black smoke-like clouds billow from chimneys of iron and sulfur, while strange ecosystems thrive in the darkness. Even today, entire communities of tube worms, clams, and bacteria survive here without a ray of sunlight, drawing their energy instead from the chemistry of the earth. For scientists studying the origins of life, hydrothermal vents are windows into the past. Billions of years ago, these cracks in the seafloor may have offered the perfect conditions for life to begin. The energy from Earth's core provided heat and motion. The minerals brought up from the mantle provided the raw ingredients, and the constant mixing of hot and cold water created gradients, chemical contrasts that could drive the formation of complex molecules. Out of this interplay, simple building blocks like amino acids could have assembled, slowly joining into more complex chains until something living emerged. One of the most intriguing ideas is that life began in the tiny pores of vent structures. These natural labyrinths of rock create microenvironments, each acting like a miniature laboratory. Inside, molecules could concentrate, react, and grow more complex without being swept away by the open ocean. In these sheltered chambers, energy from the core might have given the first push towards self-replicating chemistry. The role of Earth's heat in this story cannot be overstated. Without the geothermal energy rising from within, the planet might have been a still, cold world, with oceans lying quiet above unbroken crust. Instead, the restless interior cracked the seafloor, drove water deep into the mantle, and returned it transformed. The earth itself became a kind of engine, not only shaping landscapes, but also stirring the ingredients of life. Even today, we can see echoes of this beginning. The microbes that thrive in hydrothermal vents are among the most ancient forms of life, able to survive in temperatures and pressures that would destroy most organisms. Some of them use chemical pathways so primitive that they are thought to resemble the earliest forms of metabolism. Studying these creatures gives scientists a glimpse of what life might have looked like billions of years ago, when the only energy available came from the planet's hidden heart. The connection between the core and life extends beyond the vents themselves. Without the heat from within, plate tectonics would not exist. Continents would not drift, mountains would not rise, and volcanic gases would not replenish the atmosphere. The cycle of carbon and water between the surface and the deep earth, essential for climate stability, depends on the energy born in the core. In this way, the very possibility of life was nurtured by processes that began thousands of miles below our feet. It is humbling to think that the warmth we feel from sunlight is only part of the story. Beneath every step, heat has been flowing upward since the birth of the planet, shaping oceans, driving storms, and perhaps sparking the chemistry of life itself. The deep earth is not just a stage on which life appeared. It may have been the hidden hand that lit the first flame. The same hidden forces that may have sparked the first flicker of life have also, at times, nearly erased it. Deep in the mantle, currents of heat rise slowly upward, driven by the restless energy of the core. Most of the time, this movement is steady, breaking the crust into shifting plates and feeding the volcanoes that dot the surface. But every so often, the power builds into something far more dramatic. From the depths of the mantle, immense plumes of molten rock can surge upward in pulses that last for millions of years. When these plumes break through the crust, they create floods of lava so vast that they can cover entire regions of the planet. These are called flood basalt events, and they are among the most devastating forces Earth has ever unleashed. One of the most famous examples is linked to the extinction of the dinosaurs. Around 66 million years ago, an asteroid struck the Yucatan Peninsula, carving the Chicxulub crater. That impact is often remembered as the main cause of the dinosaurs' demise, but evidence shows that at the same time, massive volcanic eruptions were flooding what is now India with waves of lava. These eruptions formed what we call the Deccan Traps, a region that even today stretches across hundreds of thousands of square miles and reaches thicknesses of more than a mile. For nearly a million years, the Deccan eruptions spewed not only molten rock, but also vast amounts of carbon dioxide and sulfur gases into the atmosphere. The climate wavered between extremes, the skies dimmed with ash, and ecosystems already weakened by the asteroid impact collapsed completely. The combined strike of rock from the sky and fire from the depths sealed the fate of the great reptiles that had ruled the earth for more than 150 million years. Even more catastrophic was an event that occurred much earlier, about 250 million years ago. This was the Great Dying, the most severe mass extinction in Earth's history. More than 90% of marine species and 70% of land species vanished. At the heart of this catastrophe were the Siberian traps, an eruption so immense it dwarfs most others in the geological record. Over the course of nearly a million years, enough lava poured out to bury much of modern-day Siberia under layers several miles thick. The gases released into the atmosphere transformed the planet's climate, raising temperatures, acidifying the oceans, and stripping oxygen from the seas. Life teetered on the edge of collapse, and for a time, the world was nearly silent. What makes these events so striking is that they were not caused by impacts from space or by forces outside the Earth. They were born from the hidden heat of the core, rising upward in immense plumes that reshaped the surface and rewrote the course of evolution. The same currents that power plate tectonics and feed ordinary volcanoes can, under rare conditions, erupt with a force so overwhelming that they reset life itself. The fingerprints of these catastrophes are still visible. In India, the Deccan Traps form step-like plateaus of hardened basalt, their black cliffs stretching to the horizon. In Siberia, ancient lava fields lie buried beneath forests, reminders of the planet's greatest upheaval. These landscapes are monuments to the power of the Earth's interior, carved not by rivers or glaciers, but by molten rock poured out from the mantle in volumes beyond human comprehension. It is unsettling to realize how closely the fate of life is tied to the deep earth. Creatures evolve, flourish, and vanish, not only because of the surface conditions we can see, but also because of processes that rise unseen from thousands of miles below. The core, hidden in darkness, has shaped extinction and survival alike, deciding through its restless motions when eras end and when new ones begin. Every so often, the earth shudders, plates grind against one another, faults slip, and the surface shakes with sudden force. For those who feel them, earthquakes are terrifying reminders of the power beneath our feet. But to scientists, they are more than destructive events. They are messages. Every tremor sends waves through the planet, and in those ripples lie clues about the structure of the deep earth. Earthquakes are, in a sense, the only voices the planet has, whispering from the crust all the way to the core. Seismic waves travel in two main forms. Primary waves, often called P waves, move through both solids and liquids, compressing and stretching matter as they go. Secondary waves, or S waves, travel only through solids, shifting materials side to side. When an earthquake sends these waves into the earth, they behave differently depending on what they pass through. They speed up in dense regions, slow down in softer ones, and bend when they cross boundaries between layers. By studying these subtle changes, scientists can reconstruct a map of the unseen world beneath the crust. It was through this listening that one of the most stunning discoveries was made. In the early 20th century, scientists noticed something strange. S waves never appeared on the far side of the planet after a quake. They vanished entirely, as if something inside the Earth had stopped them. P waves, on the other hand, were slowed and deflected. The only explanation was that the outer core must be molten. S waves could not pass through it, while P waves were bent by the transition from solid to liquid. In that absence and deflection lay proof of an enormous hidden ocean of molten metal swirling nearly 2,000 miles below the surface. Later, another layer of mystery was uncovered. In 1936, Danish seismologist Inge Lehmann analyzed earthquake records and noticed that faint echoes of P waves were bouncing through the core in ways that could only be explained if a solid sphere existed within the liquid. Her insight revealed the inner core, a dense ball of iron and nickel, locked into solidity despite heat greater than the surface of the sun. From the silence of earthquakes came a discovery that transformed our picture of the planet, showing us that at its very center lies a solid heart. More recently, seismic listening has gone even further. By comparing how waves pass through the core from different angles, scientists have found signs that the very innermost region of the inner core behaves differently than the rest. The crystals of iron there appear to be aligned in a distinct direction, hinting that Earth's core has multiple layers, each formed under different conditions in the planet's long history. This inner core, as it is sometimes called, is not something we can see or touch, yet its presence is made known through echoes so faint they barely rise above noise, whispers carried from thousands of miles below by earthquakes. Every quake, no matter how destructive on the surface, enriches this portrait of Earth's interior. With networks of seismometers spread across the globe, scientists listen to the planet as though it were a vast musical instrument, each tremor a note that reveals the shape and texture of hidden layers. The Earth is not silent, it hums with vibrations, and those vibrations hold the key to its architecture. What makes this story extraordinary is how much can be known without a single drill ever touching the mantle or core. Humanity has dug less than 8 miles into the crust, yet by listening carefully to the messages carried by seismic waves, we have uncovered a world of molten seas, solid spheres, and crystal alignments at unimaginable depths. Earthquakes, terrifying on the surface, are also gifts of knowledge, the planet's own way of speaking about its secret heart. Beneath the shifting continents and restless oceans, beneath the mantle that creeps like putty and the core that swirls with molten fire, there is a source of energy that never sleeps. Earth has been radiating heat since its birth more than 4.5 billion years ago, and that hidden warmth still drives the planet today. Without it, the world would be cold and quiet, its surface frozen into silence. Instead, it is alive with earthquakes, volcanoes, drifting plates, and a magnetic field that shields life itself. The origins of this heat reach back to the beginning. When the Earth first formed, dust and rock gathered under the pull of gravity, colliding with such violence that the young planet became a molten sphere. The energy of those countless impacts was trapped inside, and though much of it has leaked away into space, some of that ancient fire remains, locked in the deep interior. It is a memory of Earth's creation, still glowing faintly after billions of years. But this leftover heat alone would not have been enough to keep the planet active for so long. Another source lies within the atoms themselves. Elements like uranium, thorium, and potassium are unstable, breaking apart over time in a process called radioactive decay. As they do, they release heat. Deep in the mantle and crust, this atomic fire burns silently, adding to the warmth rising from below. It is steady and relentless, a clockwork of decay that has fueled Earth since the earliest days. Scientists believe nearly half of the planet's heat comes from these radioactive elements, an invisible furnace hidden in the rocks. There is yet another contribution, one tied to the very heart of the core. As the outer core slowly cools, iron crystallizes at the center, adding to the inner core. Each new crystal releases latent heat, a pulse of energy that stirs the molten iron around it. This crystallization not only powers convection in the outer core, keeping the magnetic field alive, but also adds to the reservoir of heat that rises upward into the mantle. It is like a second heartbeat, quiet and slow, but essential to the life of the planet. The balance of these three sources, primordial fire, radioactive decay, and crystallization, has kept Earth geologically alive for billions of years. Heat rises from the core, flows through the mantle, and escapes through volcanoes and the slow drift of tectonic plates. It is this circulation that builds mountains, feeds earthquakes, and constantly reshapes the continents. The warmth we never feel beneath our feet is what allows the planet to remain a dynamic and evolving world instead of a silent and unchanging rock. To see what Earth would be without this balance, we can look to Mars. Long ago, Mars was active too. Evidence of ancient volcanoes, valleys carved by water, and magnetic fields frozen into the rocks shows that it once pulsed with inner energy. But Mars is smaller than Earth, only about half the size. With less mass, it could not hold its heat as well. Its primordial fire leaked away faster, its radioactive furnace dwindled, and its core cooled until it could no longer generate a protective magnetic field. Without that shield, the solar wind stripped away its atmosphere. The rivers dried, the volcanoes fell silent, and the planet became a cold desert beneath a thin sky. The contrast is striking. Earth and Mars were born from the same cosmic dust, yet one remains alive while the other has grown quiet. The difference lies in heat, the subtle and enduring warmth that keeps the mantle flowing and the core alive. Earth's heat has never died, and it is this hidden energy that has shaped the surface we live on and allowed life to thrive. The core of the Earth lies thousands of miles beneath our feet, sealed away behind layers of rock and mantle that no drill could ever reach. Its pressures are so intense and its temperatures so high that even imagining them feels like stepping into the realm of science fiction. And yet, scientists have found ways to glimpse what happens there, not by going down into the earth, but by recreating those extreme conditions in the laboratory. One of the most remarkable tools for this work is something called a diamond anvil cell. At first glance, it looks almost delicate, no bigger than a person's thumb. But inside it, scientists place tiny samples of material, often just a speck of metal or mineral. Then, using the hardest substance known to exist, two flawless diamonds, they squeeze the sample with unimaginable force. As the diamonds press together, the tiny point of contact experiences pressures equal to those deep inside the Earth's core. In these experiments, a material that looks ordinary on the surface is transformed. Iron, for instance, may begin to rearrange itself, its atoms shifting into new patterns that do not exist under everyday conditions. Nickel, silicates, and even simple compounds of oxygen behave differently when the weight of millions of atmospheres is forced upon them. These transformations provide clues about how matter acts in the mantle and the core, where the rules we know at the surface bend and change. Pressure alone, however, is not enough. The inner Earth is not only crushed but also searing hot, with temperatures rising to thousands of degrees. To reproduce this heat, scientists shine powerful lasers into the tiny cell. The beams are focused to an intense point, heating the speck of matter until it glows like a miniature sun. In that moment, the sample inside is pushed into a state that mimics the alien conditions of Earth's core. The results are studied using X rays, synchrotron beams, and other delicate instruments that can measure how atoms shift and vibrate under such conditions. Sometimes the changes are subtle, a crystal structure reorders itself, or an element becomes slightly more fluid. At other times, the results are astonishing. Iron may flow like honey. Silicates may compress into new minerals that had never been seen before. In these strange states of matter, scientists catch a glimpse of the physics that governs the deepest parts of the planet. Such experiments have revealed, for example, why the inner core is solid while the outer core is liquid, even though both are made of similar metals and both are heated to extraordinary temperatures. Under pressures of millions of atmospheres, the inner iron atoms are forced into such tight arrangements that they cannot flow, while those farther out, under slightly less pressure, remain molten. Without recreating these conditions in the lab, this balance of solidity and liquidity would have remained only a theory. Other experiments have helped to explain how the core generates the magnetic field. By studying how molten metals conduct electricity under extreme pressure and temperature, scientists have refined their models of the geodynamo, the engine that powers Earth's protective shield. These findings ripple outward into understanding not only Earth, but also other planets. The silence of Mars and the endurance of Earth can be explained in part through the insights gained from diamonds, lasers, and specks of matter studied in darkened laboratories. What is striking about these experiments is their scale. The entire setup can fit on a table, and the sample studied might be invisible to the naked eye. Yet what it reveals is the behavior of a world-spanning ocean of molten iron, thousands of miles deep. It is a reminder of how vast mysteries can sometimes be unlocked through the smallest of windows. By recreating the impossible, even in miniature, science has begun to peel back the layers of Earth's secret heart. The diamonds press, the lasers burn, and in that brief moment, we see a reflection of the alien conditions below our feet. Each experiment is not just a test of physics, but a conversation with the planet, asking questions that only the deep Earth can answer. The Earth's heart is not silent. It turns and stirs, molten metal flowing in slow currents thousands of miles beneath our feet. These movements, though hidden from sight, give rise to something that shapes every breath we take and every drop of water that stays bound to our planet. The flowing iron of the outer core generates a vast magnetic field, a shield that extends far into space, deflecting the solar wind that streams endlessly from the sun. Without this invisible armor, our atmosphere would be stripped away grain by grain, like dust caught in a storm. The shield is not constant. Records locked in volcanic rocks tell us that the field has flipped many times before. What was once north has become south, then shifted back again, over and over across deep time. During these reversals, the field weakens, sometimes to a fraction of its usual strength, leaving the planet's surface more exposed. Even in those weakened states, life has endured, but the thought lingers of what might happen if the dynamo itself were to falter completely. The dynamo depends on motion, on the swirling of liquid iron and nickel in the outer core. Heat rising from the growing inner core stirs these metals like a spoon through molten glass, and in their motion, electricity flows, generating the field that saves us. If the heat source ever fades, if the motion still, the shield would die. Mars once had such a shield. Evidence on its surface shows ancient river valleys, dried lake beds, and minerals formed in water, yet billions of years ago, its core cooled too quickly. The dynamo failed, the field collapsed, and the solar wind swept away most of its atmosphere. Mars became the cold, barren desert we know today. Could Earth ever share that fate? The answer lies not in fear, but in patience, for the processes that drive the dynamo are slow beyond human imagination. The inner core grows grain by grain as the planet cools, releasing heat and stirring convection in the outer liquid metal. This process will not end for billions of years, yet the thought of its eventual silence lingers in scientific minds. Without the field, the Earth would no longer hold its atmosphere tightly against the sun's constant breath. The skies could thin, the oceans shrink, and the climate we rely upon could unravel. Some scientists study subtle variations in the field, wondering if changes deep inside the core might already ripple outward to influence the surface. A weakening shield could alter the amount of cosmic radiation reaching the atmosphere, nudging weather systems in ways still poorly understood. Shifts in the field might affect how the upper atmosphere behaves, which in turn could cascade into changes in climate patterns. These ideas remain speculative, yet they remind us that what happens in the deepest heart of the Earth is never entirely separate from the world above. Our present climate is held within a delicate balance. The greenhouse gases that warm the air, the circulation of the oceans, the tilt of the planet's axis, and the reach of the magnetic shield all weave together into the fabric of habitability. Most of these factors shift over centuries or millennia, but the shield is older than life itself, standing watch for billions of years. It has endured reversals, weakening phases, and wandering poles, yet always it has returned with strength. Still, scientists keep listening, measuring, and modeling because the shield is as vital as the ground we walk on. The future climate of Earth is often discussed in terms of carbon and rising seas, but beneath those immediate concerns lies this deeper, slower story. If the core remains alive and the dynamo continues to turn, the planet will keep its cloak, protecting air and water from the stripping winds of space. If one day it fades, our descendants may live on a quieter, colder Earth, much like Mars. For now, the molten ocean at the planet's center still swirls with energy, and the magnetic shield continues to stretch into space like an unseen guardian. The story of climate, life, and habitability is tied not only to the winds above us, but to the fire below, the restless heart that has never stopped beating since Earth was born. Deep beneath our feet, the Earth's heart has been restless for billions of years. Heat rises from the core like a slow breath, keeping the outer layers alive with motion. This hidden fire powers the magnetic field, drives volcanic outbursts, and fuels the shifting of continents. But like all fires, even this one cannot last forever. The story of the Earth is one of birth, growth, and change, and it also carries within it the quiet inevitability of cooling. The core today is divided, with a liquid outer layer swirling around a solid sphere at the very center. That inner solid heart is slowly growing, crystallizing iron as the surrounding metal loses its heat. Grain by grain, atom by atom, it expands. One day, far in the future, the entire core will harden. The once vast ocean of molten iron will be no more. In that moment, the dynamo that has spun for billions of years will fall silent. Without the swirling flow, the magnetic field will vanish. The magnetic shield has long been our unseen guardian, stretching into space to protect us from the solar wind. Without it, Earth would face the full force of the sun's constant stream of charged particles. They would peel away the atmosphere, carrying molecules into space the way a river carries leaves downstream. What is left would thin and weaken until the air above became fragile. The oceans, too, would change. Exposed to direct bombardment, the upper layers of water would slowly drift away into space. Ultraviolet light from the sun would split molecules apart, leaving hydrogen to escape and oxygen to linger in unstable forms. Over immense spans of time, seas that once stretched across the world would shrink into scattered remnants, and coastlines would retreat until the familiar blue planet no longer lived up to its name. The land would grow colder as heat within the mantle faded. Volcanoes would fall silent, mountains would no longer be pushed upward by restless tectonic plates, earthquakes would cease. The very surface of the planet would stiffen, becoming frozen in place. The Earth would no longer be alive with movement, but would harden into stillness. Mars offers a glimpse of this fate. Once it too had rivers and a thick atmosphere, but its core cooled more quickly than Earth's, its smaller body unable to hold heat as long. When the dynamo shut down, the magnetic shield collapsed. The solar wind swept its air away, leaving behind the dry, thin skies we see today. Now the red planet is silent, its volcanoes extinct, its once flowing water trapped as ice or lost to space. In Earth's far future, our world may come to resemble that same quiet desolation. This end will not come soon by human reckoning. The cooling of the core moves at a pace measured not in centuries, but in billions of years. Long before the dynamo fails, the sun itself will have changed, swelling into a red giant and remaking the solar system. Still, the thought that the inner fire will one day grow still adds a note of melancholy to the story of our planet. The beating heart that has shielded life since its beginning carries within it the certainty of an ending. Yet for now, the molten currents still swirl, the field still stretches outward, and the surface still trembles with life. The earth is not finished. It is still a world in motion, still alive with fire and breath. The long cooling is part of its destiny, but that destiny waits in the farthest reaches of time. When we look to our planetary neighbors, we find echoes of what Earth might one day become. Each world carries scars of its past and secrets of its inner heart. To understand our own future, it helps to see the fates of others, silent witnesses to cosmic time. Mars, the red planet, tells one of the clearest stories. Billions of years ago, it was not the dry and frozen desert we see today. Evidence of ancient riverbeds, lake shores, and even deltas carved into its surface shows that water once flowed freely across its plains. For such water to exist, Mars must have once held a thicker atmosphere, capable of trapping warmth and shielding the surface from the raw violence of space. But that protection was temporary. Mars was smaller than Earth, with less heat locked in its core. Over time, its molten heart cooled too quickly. The dynamo that had once spun and generated a magnetic shield fell silent. Without it, the solar wind streamed directly onto the planet, stripping away the atmosphere molecule by molecule. In this slow unraveling, Mars lost its warmth, its oceans, and much of its chance to sustain life as we know it. The rivers dried, the air thinned, and the planet hardened into stillness. What remains today is a frozen world where dust storms sweep across vast plains, and volcanoes that once towered higher than any on Earth now stand extinct, their fires long gone cold. To peer at Mars is to see a ghost of Earth's possible future, a reminder that a living core and its shield are essential for a world to stay alive. Mercury, the closest planet to the Sun, tells a different story. Though much smaller than Earth, it carries a surprise deep within. Beneath its cracked and scarred surface lies a core that makes up more than half of its entire volume, far larger in proportion than Earth's. This immense metallic heart hints at a violent history. Some scientists believe that Mercury may have once been larger, but in its earliest days, a colossal collision with another body stripped away much of its outer rock, leaving behind a world dominated by its core. Even today, parts of Mercury's core may still be molten, though far less active than Earth's. Strange magnetic signatures have been detected around the planet, faint compared to Earth's shield, but proof that something deep inside still stirs. The mystery of why Mercury, so small and so close to the heat of the sun, has managed to hold on to part of its inner dynamo continues to puzzle researchers. Its surface is silent, its craters frozen in time, yet the planet carries within it a secret of survival, an enigma wrapped in metal and fire. Comparing these worlds to our own highlights the delicate balance that keeps Earth alive. Earth is large enough to hold its heat for billions of years, yet not so large that it has cooled too slowly. Its liquid outer core still spins, generating the field that stretches outward to shield us. Unlike Mars, our dynamo endures. Unlike Mercury, our surface is not stripped to bare rock but softened by oceans, air, and life. The differences remind us that habitability is fragile. A world can be lost through cooling, as Mars was, or shaped into something alien through early violence, as Mercury was. Earth's endurance is not guaranteed by chance alone, but by a chain of cosmic conditions that align just right. The balance of size, distance from the sun, composition, and inner fire all work together to create the only world we know that is still geologically alive and wrapped in an atmosphere capable of sustaining breath. The ghosts of Mars and Mercury show us what happens when that balance falters. One lost its shield and with it its seas. The other carries a massive heart, but one that beats too faintly to protect it. Earth continues to endure, its fires still churning, its fields still stretching outward into space, holding back the invisible storm of the solar wind. For now, we remain on a planet alive with motion, sheltered beneath an unseen cocoon of magnetism, while just beyond us lie worlds that could not hold on. Far beyond the orbit of Earth, where sunlight fades to a faint glow, two enormous worlds dominate the outer solar system. Jupiter and Saturn, the gas giants, are unlike anything we can truly picture from daily life. They are not solid worlds like Earth, but vast spheres of swirling gas and crushing storms, each one so large that hundreds of Earths could fit inside. Yet even in these alien realms, their hidden hearts whisper clues about the nature of planets everywhere. At first glance, Jupiter seems endless, a world of stripes and storms, with its famous great red spot spinning for centuries like a hurricane without end. But deep inside, beneath the clouds of ammonia and water, beneath the endless layers of hydrogen and helium, lies something stranger than anything found on Earth. Under pressures millions of times greater than at our surface, hydrogen is forced into a form called metallic hydrogen. In this exotic state, hydrogen behaves not like a gas but like a metal, capable of conducting electricity. This metallic hydrogen flows in vast oceans deep beneath Jupiter's clouds, generating one of the most powerful magnetic fields in the solar system. At its very core, scientists believe there may be a dense heart of rock and ice, perhaps several times the size of Earth, wrapped in this alien sea of metallic matter. Saturn, with its elegant rings stretching across space like cosmic jewelry, carries a similar secret. Though lighter and less dense than Jupiter, Saturn too is thought to hide a metallic hydrogen interior. Seismic ripples measured in its rings suggest that Saturn's core is not neat and tidy, but instead a blurred region where rock, ice, and metallic hydrogen mix in gradients rather than layers. Its magnetic field is more symmetrical than any other planet, a puzzle that scientists are still struggling to explain. What stirs deep inside Saturn may hold the key to understanding how magnetic shields can vary so widely between worlds. The study of these hidden cores goes far beyond our solar system. When astronomers peer at exoplanets orbiting distant stars, they often detect giants even larger than Jupiter, worlds called hot Jupiters that sit so close to their suns that their atmospheres boil away in fierce stellar winds. By comparing these alien worlds with Jupiter and Saturn, scientists can imagine what their interiors might be like. Some may have cores crushed into states of matter that do not exist anywhere else, with exotic metals and ices layered in ways we cannot yet reproduce in laboratories. Others may have lost their inner order entirely, their cores dissolved into turbulent seas of gas. The lessons we learn from Earth's own depths provide the foundation for these guesses. Our understanding of pressure, heat, and the behavior of elements under crushing conditions helps scientists model what might lie inside alien worlds. Just as seismic waves reveal Earth's hidden structure, so too do the subtle signatures of starlight passing through exoplanet atmospheres hint at what lies far beneath. Earth, with its molten outer core and solid inner sphere, becomes a kind of Rosetta Stone for decoding the invisible interiors of planets we will never touch. The scale may differ, yet the pattern feels familiar. Earth has a mantle of flowing rock. The gas giants have mantles of hydrogen that shift from gas to liquid to metal under pressure. Earth has an iron heart that generates its magnetic shield. Jupiter and Saturn have oceans of metallic hydrogen driving magnetic fields so immense they carve cavities in the solar wind. By tracing these similarities and differences, we see that planets across the cosmos, no matter their size or distance, share the same basic story: layers built by gravity, energy stored in their cores, and mysteries that ripple outward to shape their skies. Every discovery about these alien interiors reflects back on our own world. If metallic hydrogen can exist inside Jupiter, it shows how even the simplest element can transform under conditions of unimaginable force. If Saturn's blurred core resists neat categorization, it reminds us that nature often defies our tidy models. And if Earth, small compared to these giants, still echoes their layered complexity, it suggests that what we learn about our own depths is not just about us, but about the very architecture of planets everywhere. Even with all that scientists have uncovered about the hidden layers of our planet, some of the deepest mysteries remain unresolved. The more seismic waves we capture, the more experiments we attempt, the more questions seem to rise from the darkness beneath us. These unanswered puzzles keep Earth's story alive, reminding us that our world is still stranger and more complex than we dare to imagine. One of the most haunting enigmas rests far below the mantle at the boundary with the molten outer core. Here lie vast and puzzling features known as ultra-low velocity zones. When seismic waves from earthquakes pass through them, they slow to a crawl as though hitting something denser and thicker than the rocks around them. These blobs, some stretching hundreds of miles across, cling to the boundary like strange scars in the fabric of the deep. No one knows exactly what they are. Some scientists believe they could be remnants of an ancient planet, Theia, which long ago collided with Earth and gave birth to the moon. If true, then fragments of an alien world still sit entombed in our planet's hidden layers, carried downward over billions of years and preserved at unimaginable depths. Others think they may be chemically distinct patches of mantle, zones altered by repeated subduction of ancient seafloors that sank and pooled near the core. Whatever they are, these blobs are not small anomalies. They are titanic structures that could hold clues to Earth's earliest days, yet they remain far out of reach, hidden in the crushing dark. Another mystery lingers even deeper, at the very center of Earth. For decades, scientists thought they understood the inner core, a solid sphere of iron and nickel pressed so tightly that it resists melting even at temperatures hotter than the surface of the sun. But careful study of seismic echoes has revealed something unexpected. Deep within that inner sphere lies yet another distinct region, an inner core. Its crystals are aligned differently than those of the surrounding iron, suggesting that Earth's very heart is not uniform but layered within itself. Why does this inner core exist? Was it formed during some ancient shift in Earth's magnetic field? Is it the record of a long ago transition when the inner core first began to crystallize? Or could it hold signs of processes we have not yet imagined? The answers remain elusive, hidden within the most inaccessible place on Earth, where no probe will ever travel and no drill will ever reach. And then there are the hidden cycles of water and carbon, threads that tie the surface of our world to the crushing mantle beneath. We know that tiny crystals of ringwoodite carry water hundreds of miles below ground. We know that carbon, locked away in deep rocks, returns to the surface through volcanic eruptions. But the true amounts remain uncertain. Is there more water hidden below than in all the oceans combined? Could Earth's mantle contain enough carbon to shape the climate for millions of years at a time? These are not abstract questions. They touch directly on the cycles that make surface life possible. If the mantle holds vast reserves, it means our climate and oceans are not only products of the sky above, but also of the fires and minerals below. The Earth might be breathing in a rhythm far slower than our lifetimes, exchanging gases and water across spans of millions of years. Each of these questions lingers like a quiet riddle. What exactly are those immense low velocity blobs sitting silently at the base of the mantle? Why does the inner core hide another layer within itself, aligned like a secret code? How much of our water and carbon is tied to the deep, and how much is still waiting to rise? The tools we have today only let us glimpse pieces of these answers. Seismic waves sketch outlines, laboratory experiments hint at possibilities, but the full story remains buried. It is humbling to think that beneath every step we take, beneath every ocean and continent, lies a library of secrets that has not yet been read. The greatest mysteries of our planet are not found in the stars above, but in the hidden depths of the world we already call home. Every step we take rests on a surface thinner than we often imagine. The ground beneath our feet, the mountains that reach into the clouds, even the deep ocean floors that cradle entire ecosystems, all belong to a delicate shell that barely scratches the surface of Earth's true body. Beneath this fragile crust, fire stirs. Heat older than life itself moves in endless currents, carrying with it the power to shift continents, to raise new mountains, and to tear open the sea floor. We live on a thin skin, stretched across a planet of fire and metal, and yet that skin holds everything we know. Our homes, our forests, our rivers and cities, all balanced on less than 1% of Earth's vast mass. It is easy to forget that the ground we treat as steady is not steady at all. It trembles with earthquakes, bends with the slow drift of continents, and breathes through volcanoes that let the deep speak for a moment before quieting again. Life flourishes here because of this hidden energy, not in spite of it. Without the warmth rising from below, Earth would be a frozen husk drifting through space, stripped of its oceans and its air. Every moment of existence, every breath of air and drop of water is tied to forces no human hand can touch. The core spins in silence, molten iron flowing like an unseen tide, creating the magnetic shield that guards us from the sun's most dangerous storms. The mantle churns with slow currents of rock, invisible to us but strong enough to push entire continents across the globe. Even the air we breathe carries the signature of the deep, enriched with carbon and water recycled through the furnace of Earth's hidden layers. There is a paradox here, one that is both humbling and comforting. We live in the presence of immense power, yet we move through our lives with little sense of it. Children play in fields above molten stone. Cities glitter on coastlines that rest on shifting plates. We sleep in homes built atop a crust that is constantly stretching, cracking, and rebuilding. And still, day after day, the rhythm holds steady enough for life to not just survive, but to thrive. The mystery of Earth is not only in its depth, but in the way it gives without revealing itself. We cannot see the mantle, yet it shapes the continents where civilizations rise and fall. We cannot reach the core, yet its invisible dynamo shields the fragile air that wraps around our world. The planet sustains us while keeping its true body hidden from view, a secret that hums beneath every living moment. It is tempting to think of frontiers as distant, out there in the stars or on alien worlds, yet the greatest undiscovered frontier is beneath our own feet. We have charted the surface of the moon and mapped the planets orbiting distant suns, but we cannot say with certainty what lies 100 miles beneath our shoes. We live beside an ocean of mystery, silent and close, carried with us in every heartbeat. This mystery is not frightening, but awe-inspiring. It means that Earth is alive in ways we are only beginning to understand. It means that every blade of grass, every bird in flight, every breath we take is part of a larger story written in stone and fire below. The unknown is not separate from us. It is the ground we stand on, the force that makes our lives possible. To live on Earth is to live on a mystery, one that cradles us and challenges us in equal measure. The crust may be thin, but it carries the weight of oceans and forests, dreams and histories, all balanced above a world of fire. And while we may never see its full depth, its unseen power is written into the air we breathe and the soil we touch. In every sense, Earth itself is our greatest undiscovered frontier. We have walked together across the fragile surface of our planet and looked inward into the hidden heart that no eye has ever seen. From the trembling ripples of earthquakes that act as Earth's quiet voice, to the secret oceans locked in stone, to the rivers of molten iron swirling in the dark, we have followed the clues that science has uncovered, and still we stand before a mystery that is larger than us all. It is a mystery that rests not in distant galaxies or faraway stars, but directly beneath our feet. Every step you take tomorrow, every breath you draw, is carried by a planet that is alive with fire and movement below. You may never feel its pressure, never hear its deep rhythms directly, but it is always there, steady and hidden, like the heartbeat of the world itself. Science, with all its instruments, has given us glimpses. It has told us that the crust we live on is a shell thinner than the peel of an apple, that deep crystals hold water vaster than all of our oceans, that diamonds carry whispers of places hundreds of miles below, and that the very air we breathe depends on a magnetic shield born in the darkness of the core. And yet, even with all of this, the Earth remains a place of wonder, full of unanswered questions waiting quietly in the deep. Perhaps that is what makes this story so powerful. The unknown is not far from us, not light years away in another system, but here, holding us, carrying us, surrounding us every moment of our lives. The ground may seem steady, but beneath it flows a hidden world that shapes the mountains, steers the oceans, and decides the fate of every living thing. So it is worth asking, softly, as the night deepens and thoughts drift like waves, What else lies beneath, waiting to be found? Are there forces still unimagined, secrets still unmeasured, truths that will one day reshape what we think we know about the very ground we call home? The journey into the earth is not finished. It has only just begun. If you have felt a sense of calm in this slow wandering through science, I would be grateful if you gave this video a gentle like or tapped subscribe so that others might discover this quiet space as well. It helps more dreamers, thinkers, and wanderers find their way here to a place where curiosity and rest meet. And if you would like, share in the comments where in the world you are listening from tonight and what time it is there. It is always a joy to see this little corner of wonder reaching across oceans and time zones, weaving us together in ways as hidden and remarkable as the earth itself. Thank you for being part of this journey into the unseen. Thank you for letting the mysteries of science keep you company as the hours stretch onward. The earth is not just a planet we stand upon, it is a story still unfolding, a secret still whispering, and together we will continue to follow its trails, one gentle step at a time. Now let the weight of the day fall away, let the silence settle around you like a blanket, and let your thoughts drift toward the deep, where fire and stone still shape the world above.